Okay, so let's talk about acids and bases, and to do this we need to define, what compounds are acids, what compounds are bases. And these definitions have kind of evolved over time, where first got to come up with a real scientific definition other than the acids are sour, bases are bitter definition. Is a guy named Arrhenius who said that an acid is something that has H+, a base is something that has OH- in it. Okay, so an acid for Arrhenius, something like hydrochloric acid, HCl, where it has this H plus that it can donate. And then a base for him is something like sodium hydroxide, where it has that hydroxide available as well. Okay, and then what we notice though is that there are some other compounds that when they were put in an aqueous solution gave the solution a basic pH, but didn't have OH- in it. And so Bronsted-Lowry noticed that OH- is just a special case of a broader class of molecules. Okay, and so for what he noticed is that OH- is a base because it has the ability to accept this proton. Okay, and so to do that, a base for Bronsted-Lowry is a proton acceptor, and for an acid is going to be a proton donor. So this is no different. We have not changed our definition of an acid at all. We've only changed the definition of a base. And an example of one of the things that we've included now is ammonia, so NH3. Or if we look at the Lewis structure, okay, the key component that we need to be a Bronsted-Lowry base is this lone pair. So that lone pair is a site where the proton can form a single bond with the nitrogen in this case, and so it can accept that proton and form the bond. Finally, a very small percentage of things are Lewis acids, and protons are just a more specific case of a broader class of molecules, those are going to be things that are going to have fewer than an octet, or in the case of protons, going to have fewer than the duet, so the two valence electrons it would need to have a full outer energy level. So these, because of that, how they are electron poor, what they're willing to do is accept this lone pair. So as we kind of switch it around, Lewis acids then are lone pair acceptors, and bases are lone pair donors. So going from Bronsted-Lowry to Lewis bases, we're not changing them. To accept a proton, you need a lone pair. To donate, so it's really the same thing. The difference is with lone pair acceptors, you get something like BF3, where the boron has fewer than an octet, and it needs a lone pair to get that octet. Okay, so let's take a look at an example of some of these reactions. In the first case, HCl, so that is a Arrhenius, that would qualify as an Arrhenius acid, and sodium hydroxide is an Arrhenius base, and we get a neutralization reaction here where we form water and sodium chloride. So an acid and a base form water in this case, because these are both a strong acid and a strong base. Okay. Over here we have an example of more Bronsted-Lowry. In this case, so we see water is acting as an acid in this case. So ammonia has this lone pair that it's willing to accept a proton at, and water has the ability to both donate a proton and be left with OH-. So a base and an acid gives us an acid and a base. And so this is this idea of conjugates that we're going to talk about here, where ammonia and ammonium are very related. Well, if you look at our definitions, this is going to be a base, this is going to be an acid. Water in this case is acting as an acid, and it has something analogous to it. This hydroxide is similar to water. It's a base. It's acting as an acid. So these are our conjugate acid-base pairs. And an example of a Lewis acid-base reaction here is BF3, the example I used. So the lone pair, I'm going to go over here where boron needs some electrons. It's going to form a single bond, and they're just going to be bound together.